He's very active in tabla, and also he's very active in teaching.
Yes, yes.
But I have not seen him in a long time, in the last 2 years, because of pandemic.
Because of that.
So that is a problem. If he got the email, maybe he will join. I don't know. But
Nah, I texted.
okay.
I think he got the email, and he is a
Yeah. I think he
member
got
of the association. So he
right.
got
But then he has other he has to
Ah.
teach, and he has other duties and all these.
he has a lot of teaching pressure.
Yes, yes,
Yes.
yes. And more we are doing things in the evening, office hours and all those. So that takes more time now. Like after hours here, so like 8 o'clock, 9 o'clock
Okay.
in the evening, we are doing office hours online,
Okay.
so people can join. So that's a different routine.
নীতিশ কেমন আছো?
এটা ভালো 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 শ্যামাপ্রসাদ দা, ভালো আছেন তো?
হ্যাঁ, মোটামুটি ঠিক আছি।
আশা করি, I hope the talk will be good.
Sure. We'll all enjoy it.
স্যার শরীর ঠিক আছে?
হ্যাঁ, মোটামুটি ঠিক আছি এখনো। সকালে একটা টক দিয়েছিলাম, সেটা ওই ইন্টারন্যাশনাল স্ট্যাটিস্টিক্স এডুকেশন সেন্টার, যেটা ISI এর,
হ্যাঁ
ওইটা লাস্ট লেকচারটা ছিল অন মাল্টি ক্রাইটেরিয়া ডিসিশন মেকিং। গতকাল 75 মিনিট বলেছি, আজকে 75 মিনিট বলেছি।
Oh, that's long.
75 মানে অনেকটা সময়।
That's long.
একটু টায়ারিং,
হ্যাঁ
টায়ার্ড ফিল করি।
স্বাভাবিক।
সুমন্ত, আমরা কি শুরু করবো?
7টা আর 2 মিনিট দেখে নি, জাস্ট 7টা বাজে, একদম ডট 7টা, আর 2 মিনিট দেখে যাও, স্টার্ট
2 minutes. Okay.
ইমান জয়েন করেছে।
এই সময় অনেকেই জয়েন করে আর কি, এই 5 মিনিটের মধ্যে অনেকেই জয়েন করে যায়।
ঠিক।
2 মিনিট দেখে
Okay.
স্টার্ট।
অরিন্দম এসে গেছে, রাহুল তো আগে থেকেই আছে দেখছি। 45 others. আজকে বিকাশকে দেখছি না।
হ্যাঁ দেখতে পাচ্ছি, উনি হয়তো জয়েন করবে, এখন জাস্ট 7টা 1। একদম শুরু করে দিই, মানে 65 হয়ে গেছে না?
হ্যাঁ,
অনেক হয়ে গেছে।
ইমান,
হ্যাঁ
আমার মনে হয় শুরু করে দেয় ভালো, 66 প্রায়।
ওকে, তোমরা কি রেকর্ডিং শুরু করো?
হ্যাঁ, রেকর্ডিংটা
হরে কৃষ্ণ।
রেকর্ডিংটা প্লিজ স্টার্ট কর।
তাহলে শুরু করবো?
রেকর্ডিংটা আমার মনে হয় স্টার্ট হয়নি, কেন লাল
হয়নি,
দাগটা
আচ্ছা,
একটু
লাল
সময়
দিয়ে
লাগে, আর 1 মিনিট হয়তো সময় লাগবে।
Okay.
1 মিনিট সময় লাগবে। হ্যাঁ,
Okay.
বিমান।
We welcome all of you to this lecture series for propagation of statistics education and research organized by Calcutta Statistical Association as a part of its outreach program. Calcutta Statistical Association was established in 1945 by a group of statisticians who were members of the teaching staff of the Department of Statistics, University of Calcutta. From the very onset, the objective of the association has been to promote activities related to statistics. Using its limited resources, the association continues to play a key role in developing statistics. This lecture series is being organized as a part of celebrating 75 years of CSA's glorious existence. The association has always focused on advancement and dissemination of knowledge of statistics through its various publications. The Calcutta Statistical Association Bulletin, from the very beginning, paid due attention to quality of articles. Today, the bulletin is highly rated by the international community of statisticians. Since 2016, Calcutta Statistical Bulletin is being published by Sage Publications. The association regularly organizes lectures by eminent scholars from India and abroad. Since 1991, Calcutta Statistical Association, jointly with the Department of Statistics, University of Calcutta, is organizing an international symposium on probability and statistics every 3 years. It's now time to introduce our speaker for today. We are really honored that we have with us today Professor Nitish Mukhopadhya, Department of Statistics, University of Connecticut, Stores. Professor Nitish Mukhopadhya received his PhD degree from the Indian Statistical Institute, Calcutta in 1975. He has been a full professor in the Department of Statistics at the University of Connecticut, Stores since 1985. He served as the head of the department during 1987 to 1990. Prior to joining the University of Connecticut, Stores, Professor Mukhopadhya taught at various scholarly institutions, including Monash University, Melbourne, University of Minnesota, Minneapolis, University of Missouri, Columbia, and Oklahoma State University. He has made prolific contributions in many areas, including statistical inference, parametric and non-parametric, sequential analysis, multiple comparisons, clinical trials, applied probability, econometrics, and applications. Professor Mukhopadhya is especially recognized for path-breaking contributions in sequential analysis, as well as selection and ranking. His honors include elected fellows of the Institute of Mathematical Statistics 2002, the American Statistical Association 2003, the American Association for the Advancement of Science 2012, elected ordinary member of the International Statistical Institute 2007, elected member of the Connecticut Academy of Arts and Science 2014. He received the Abraham Wald Prize in Sequential Analysis 2008, the Don Owen Award 2015. He has been the editor-in-chief for the premier journal Sequential Analysis since 2004 and serves as an associate editor for a number of other leading international journals. Professor Mukhopadhya is the author or co-author of 6 books, 15 book chapters, more than 250 research papers, and editor or co-editor of 6 special volumes. He has supervised more than 25 PhD students as their major advisor. Professor Mukhopadhya also has keen interest in literature and music. He is one of the founding members of a cultural club in Connecticut called Shur O Chondo. Professor Mukhopadhya has always been closely associated with Calcutta Statistical Association. He has visited in almost all the editions of the International Triennial Calcutta Symposium on Probability and Statistics. Professor Mukhopadhya is presently one of the vice presidents of the association. We are really grateful to Professor Mukhopadhya for accepting our invitation to deliver this lecture. May I now request all the participants except the speaker to kindly turn off your microphones. Please write your questions to the speaker in the comment box only. We'll have a discussion session at the end of the lecture. I'll now request Professor Mukhopadhya to begin his presentation.
Thank you, Divan, and thank you to everyone. So let me share my screen and then I will begin my talk. I'm not very computer savvy. Can you all hear me? Can you all
Yes, sir.
hear me okay?
Yes,
Okay.
yes, we can hear you.
Is it okay? Volume is all right?
Absolutely, okay, sir.
It is fine.
Okay.
It is fine.
So I'm not computer savvy at all. So I will try to do my best. Shumanto, Dhiman, Shaptorshi, and other younger colleagues have helped me to get to this stage. So I hope I will give a good lecture for, especially for younger colleagues and students and young researchers and so on. So let me upload my talk. So now, okay. How do I get there? Let me see. Is that the one? I have my screen open.
The Google Meet screen is open now.
Yeah, Google screen. You can see me so that your screen is open. So I'm going to present now,
So you please click on
and
present
then
now.
I will go to my entire screen.
Yes,
that
yes,
option.
Okay, okay.
Right, sir.
I hit that, but then I cannot see my screen.
So your entire screen, then you click on entire screen, then a window will open. Share
The
your
window is
entire
open,
screen.
but I cannot see my screen there, so that I cannot select that.
সুমন্ত তুই প্রেজেন্ট করে দে।
No, I have to do it from here. Otherwise, I cannot go back and forth.
Right.
Yes, yes.
Let me see. When I practiced last time, it was there, right? Let me try this. Let me try this. Share window. Will that work? Yes, now it works. A window. So share. Can you see that now? Can you see that now?
Yes, sir.
Yes.
Yeah.
Can you also hear me?
Yes.
All right. Okay. So this is all right then, right?
Okay. Now it is fine.
Okay. All right. Okay. So let me begin. This is just about 9:40 here, 9:40 or so. I'm going to talk about this particular topic I call pairwise independence, mutual independence. I will show some new illustrations and a generalization. And so let me see how it goes, and I will explain why I am doing this. And hopefully I will get a lot of questions at the end. All right. So pairwise independence and mutual independence. Let me go to the next slide. Introduction, and let me tell you at the outset that the lecture is supposed to be simple. I'm not doing anything esoteric. Very simple presentation. So especially students should understand everything. Actually, more than I do. So let me keep it at that level. So consider three random variables, x1, x2, x3, and respective PDFs I call FI, XI. So they are not IID, or I'm not saying anything about their independence or dependence. So they have the marginal distributions FI, XI, and supports are x1, x2, x3. They're unrelated. And I give here an example. It may be x1 is 0 to 1, x2 may be 0 to 1, x3 may be -1 to 3. They're unrelated. Not, for example, x1, x2, x3, 0 to 1, but x1 is less than twice x2, less than x3, less than 1, and x1 is positive. That's what I call related intervals, okay, or related spaces. In those situations, almost always x1, x2, x3 are dependent. You can show fairly easily. But I'm taking kind of freelancing intervals, x1, x2, x3, separated intervals, so there is no confusion. And Fi, Xi's are densities there. Okay. First definition of pairwise independence, if you are not familiar, pairwise x1, x2, x3 are pairwise independent. We say that if and only if xi, xj are independent. So each pair is supposed to be independent out of 3. So x1, x2 will be independent, x1, x3 will be independent, and x2, x3 will be independent. If that happens, we say the collection x1, x2, x3 are pairwise independent. An independent pair means the joint distribution of xi, xj, that is Fij, xi, xj, that is the product of the two single marginals for all xi, xj in the appropriate spaces. All right, and that has to be the case for all I not equal to j. That means pairwise independence. What will be mutually independence? Mutually independence means every subset is independent. So x1, x2, x3 are called mutually independent if and only if the xi's are pairwise independent, which I have defined just now, and also the joint distribution of x1, x2, x3, they factorize into f1, f2, f3 for all x1, x2, x3 in the appropriate space, x1 cross x2 cross x3. So just joint density being product of each marginal may not mean they're independent. So may not mean they're mutually independent or independent. Sometimes we drop the word mutually, all right? So they have to be pairwise independent. So those are the subsets, pairwise subsets. There will be 3 of them. And also all 3 density, joint density for the 3 random variables, that will factorize into 3 separate pieces, f1, f3, f3 for all x1, x2, x3. So that is the definition. That's what we are going to talk about. Pairwise independence, mutual independence, and pairwise independence may not imply mutual independence. So first, some simple ideas for, I think, students may like it. And again, it's not very difficult. Begin with any interval, non-negative integrable function on any interval. So you have to start with non-negative integrable function. So I require in this talk just basic, simple integration. All right. Again, nothing esoteric. So students, young researchers, just relax. So we take some intervals, you take any interval you want, and think of a non-negative integrable function there. And then what you do is just normalize it. For example, here is an example, x squared. I start with x squared on 0 to 1. Very easy function. You integrate it, very easy. And so you can see that the integral is 1/3. So I have to multiply x squared with 3. Now that becomes a PDF between 0 to 1. Outside will be 0. This is a non-symmetric PDF on 0 to 1. All right. Next one is I took another function, x times 1 plus 3/4 x. You can pick any function you want as long as it's non-negative on the support. All right, so this is integrable, non-negative, of course, between 0 to 1. And then if you integrate, again, very, very simple, you integrate it and it comes out 4. Very simple integration. All right, and then, so you have to divide this by 1/4, and that becomes a PDF on the interval 0 to 2, and you define 0 outside. This is also a non-symmetric PDF on 0 to 2. There is a typo here. This is interval 0 to 2, all right? Now, it doesn't mean you have to get only non-symmetric functions. You can get symmetric functions also. For example, now C, start with absolute value of x raised to the power 3 over 2. I just take them almost like randomly, any function I want. Doesn't really matter, as long as it's integrable, non-negative. So this function is integrable between -1 to 1, and it is, of course, non-negative, absolute value of x. And you integrate it, and that comes out as 4 over 5. So you multiply this by 5 over 4 on the interval -1 to 1. Now it becomes a PDF, and it's a symmetric PDF. So you have a lot of freedom, all right? In this lecture, everybody has a lot of freedom to pick almost any densities you want, but naturally I cannot interact with you, so I will give you my specific densities, but they're nothing special, all right? So first example, pairwise independence may not imply independence, a classical example. So textbooks, most textbooks, not all, nobody can check all textbooks. I check many textbooks. Textbooks often recycle one classical example with minor modifications. That's it. So let me explain that example. Classical example with minor modifications that almost every textbook includes. So toss a fair coin 2 times. A fair coin 2 times. So sample space is like here, head, 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 tail, tail, head, tail, tail. Each one has 1/4 probability because the coin is fair. And then define A1, head, 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 tail. That means first toss is a head, and then head, head, tail, head. That means second toss is a head. And A3 is head, head, tail, tail. That means both are same, either head, head, or tail, tail. Now, P of A1 is, of course, 1/2, 1/4 plus 1/4. P of A2 is also 1/2. P of A3 is also 1/2. Very simple calculations, okay? You can do with your eyes closed. And now if you take A1 intersection A2, you have only HH. So that will be 1/4. P of A1 intersect A3, again, you have only head, head included. That will be 1/4. And P of A2, A3, also you have only head, head. That will be 1/4. So you can see P of AI, AJ is P of AI times P of AJ for all I not equal to J. So these AI, AJs are pairwise independent. They are not random variables. They are not random variables. They are events. Okay, that's what we call them, right? So they are independent, pairwise independent events. Now I will show you how easy it is to show that, first of all, A1, A2, A3 are pairwise independent, but they are not independent. For example, A1, A2, A3 joint probability P of head, head, because only head, head belongs to all three. So that is 1/4. So joint probability of A1, A2, A3 is not product of P of A1, P of A2, P of A3, because that should have been 1/2, 1/2, 1/2. So it should have been 1/8. So A1, A2, A3 here are not mutually independent. But again, I will remind you, they are events, not random variables. So here are random variables. I define xi as indicator function of AI. Now AI is an event. So indicator function of AI means it is either 1 or 0. 1 if AI occurs, 0 if AI complement occurs. So now xi becomes a random variable. And you see immediately that they are Bernoulli random variables, but they're random variables nonetheless. So you have x1, x2, x3, 3 random variables I have defined. Now you can show easily, because I have already shown that x1, x2 are independent, x1, x3 are independent, and x2, x3 are independent, pairwise. So they are pairwise independent. But x1, x2, x3 are not independent. I've shown that already, all right? So here is an example where you have 3 random variables that I'm working with, and They are pairwise independent. All pairs are independent because distributions factorize for 2 at a time. But as soon as you take 3, things are messed up and they are not independent. So this is the classic example, basic example included in practically as many textbooks as I could check. Okay, and unfortunately, that's it. That's it. Okay, one example. One example. Of course, it has variations. You can have many variations of this. Like for example, you can toss a coin. You can toss a roll of a dice and count the even integers or odd integers. Now it comes in under my setup. It becomes Bernoulli. So so books give, like, they pretend they are giving different examples, but they don't. They give the same example. It just paint it a little bit differently. But I don't like that. I don't like that very much. Students and other young researchers may enjoy considering and exploring a whole lot of other kinds of examples. That's my experience from last 45 plus years. If one example doesn't work, give another example. If that doesn't work, give another example. If that doesn't work, give another example. Sometime it will hit you, all right, and you will see, oh, that's what is going on. So hence, what I'm going to do will exhibit a broad set of simple constructions of new and non-trivial pairwise independent random variables, which are not mutually independent. All right. So once you see my examples, you will see you can construct hundreds of them, thousands of them, millions of them, and you can ask students to manufacture them. It's absolutely no problem. So I would say just relax, everyone. Okay. I'm here to tell you that simple stuff can be more pretty than one may realize. It may look simple, but probably, hopefully, it is not simple. All right. When things look simple, it can also be you may not realize how simple it is. Some of you, and some of you may realize it is trivial, but that takes some maturity and so on. So let's go on. Pairwise independence may not imply independence. New classes of examples. So this is my first class of new examples, class 1. All right. So consider 3 arbitrary positive integrable functions, AIX. All right, and I showed you in the earlier slide, in my second slide or whatever, you can construct you can take any arbitrary integrable non-negative function and make a density out of it. So think of AIX as a density between 0 to 1. All right, that's all my demand. That's my only demand. All right. So consider 3 of them. They're all defined between 0 to 1. And now I said easy does it. All right. Don't make it complicated, because if you cannot integrate that fast, that quickly, that efficiently, don't make it complicated. All right. Make it easy. So I consider x1, x2, x3, 3 random variables now, and create a function of 3 variables. So I have a1, x1, a2, x2, a3, x3, because remember, I have my functions, AIX. So instead of x, I plug in x1. I have a function of x1 with I equal to 1. With I equal to 2, I plug in x2. I have another function that's for x2, and for 3, I equals 3. I have a3, x3, and then so those are my functions. And now look at this function, f3x. This is a bold x, so that is x1, x2, x3. I define as 1/4 a1 x1, a2 x2, a3 x3, product of all 3, plus a1 x1, plus a2 x2, plus a3 x3. And remember, keep in your mind, in the back of your mind, you can pick any a1, a2, a3, any functions, as long as, for this example to work, between 0 and 1, but you can modify it. I always like to do simple things. So f3x is, of course, non-negative. It is positive in 0, 1 cube, 0, 1, 0, 1, 0, 1. Now, the superscript 3 indicates that it's a function of 3 variables. That's all. So don't get nervous. So f3x means it's a function of three variables. That is just line of communication between you and me. All right. The superscript means that. And now you want to check few things. Like if you want to integrate this whole function, three variable function, between 0 to 1, that's the integral there. So you can see 1/4 will be 1/4. And then A1, A2, A3, I'm integrating each one between 0 to 1, 0 to 1, 0 to 1. So it will be 1 because each is a density. And then A1, X1 will give me 1. But A2, A3, they're defined between 0 to 1, 0 to 1. So that will still be 1. A2, X2, with respect to X2, the integral will be 1. But there is no X1, X3, but they're defined between 0 to 1. So that will be 1. And similarly, this will be 1. So this will be 1, this will be 1, integral, this will be 1, this will be 1, or the whole space, 0, 1 cube. So it will be 1/4, 1 plus 1 plus 1 plus 1, 3. So that is 4, so that is 1. So it's a non-negative function on 0, 1 cube. And so it's a PDF, joint PDF on 0, 1 cube. Outside, of course, I'm defining is 0. That's automatic. I did not write that, but it is defined only on 0, 1 cube. Now I just conceptualize three random variables, x1, x2, x3, whose joint PDF is this function, f3x on 0, 1 cube. I just pick them from top of a tree. Doesn't matter where you pick it from. Think of x, because they're densities. You can consider random variables x1, x2, x3s with that density. All right, with joint density this one. All right. So now what happens? Just see what happens. One-dimensional marginals will be you have to integrate the other two variables out. Very simple. So if you want the ith variables marginal, so xi, so that means you have to integrate with respect to xj, xk. So you are going to integrate with xj, xk. So going back here, for example, if you integrate with respect to x2, x3, this part will fall apart. You will have a1, x1. This will give you a1, x1. Again, between 0 to 1. A2, x2 will give you 1 integral. A3, x3 will give you 1. So this will be a1, x1 from here, a1, x1 from here, 1 from here, 1 from here. So you will have 1/4 aixi plus 2. So this is integration with respect to xj, xk for any I not equal to j or not equal to k. So this is the marginal of xi. On this space, this is not 0, 1 cube. This will be xi in 0, 1. Okay, so there's a typo here. I apologize for that. So for all x in 0, 1, 0, 1. So this is the marginal. So it has to be on 0, 1, not 0, 1 cube. So that's a obvious typo. So similarly, now you can, so you know all the marginals. These are the marginals. All right, no arguments. Similarly, two-dimensional marginals. So how will you get the two-dimensional marginals? Well, you have to integrate with the other variable. So if I look at xi, xj, then I have to integrate with respect to xk. So think of x1, x2, and then integrating with respect to x3. So you will have a1, a2, then you will have a1 and a2, then plus 1. Again, keep in mind that all the random variables I have defined between 0 to 1. So now this becomes 1/4, 1 plus aix, 1 and 1 plus ajxj. So this is 1 plus aixi, 1 plus ajxj, and then you can see sitting outside 1/4. So that is exactly 1/2 of 1 plus aixi and 1/2 1 plus ajxj. That means it factorizes. All right, that's the beauty of this construction. So xi, xj for any I not equal to j, they are pairwise. They are pairwise independent, obviously. So they are pairwise independent, no problem. All right, for any ij not equal between 1 and 3. But the full collection x1, x2, x3 cannot be independent. Why not? Because look at look at my F3x, the joint distribution. If you are multiplying 1 plus A1, 1 plus A2, 1 plus A3, where is A1, A2? You don't see that. That has to appear somewhere. Where is A2, A3? You don't see that. All right. So obviously some terms are missing. So 1 plus A1, 1 plus A2, 1 plus A3 times 1 half, 1 half, 1 half is never going to match that for some x1, x2, x3 in the cube 0 to 1. So they are dependent. So mutual independence does not imply pairwise independence does not imply mutual independence. Now just think about it, how many examples you can construct. You can construct millions of examples. Pick your A1x, A2x, A3x, all right? And you are in the game. So this simple and easily understood construct is different from all trivialities, I call trivialities, in the first classic example, that head, tail, tail, head, tail, tail. From all trivialities we initially included in section 2. This is not trivial example, but this is a pretty example, I would say, in my view. And almost, I would say, even first-year graduate student can understand it. It's not like I cannot do it. You can do it, all right? All we require is 3 arbitrary functions, non-negative, integrable on some spaces, and you adjust the coefficients. You can always adjust the coefficients. And for example, here I give 3 choices. The same functions I showed before, 2x1 in the interval 0 to 1, 3x2 squared between 0 to 1, and this function I picked before, or maybe I did not. But then you can do that. Again, there is a typo here. It's x3. So these 3 functions will work fine, as will hundreds and thousands and millions of other functions will work just as well. This particular example is in my textbook, all right? Probability and statistical inference. I know some of you may be familiar with that, all right? So I will leave it at that example at that stage. Now let me go into class 2 of new examples, all right? So again, the same idea. I will not rehash. It's boring. So I have now A1, A2, A3 between 0 to 1, just for simplicity, because if you have between 0 to 1, when x2 is missing, the integral is 1. That's why. But you can take 0 to 2 and then multiply by 1/2. It will still be 1. So here the function is little more complicated. 5 times A1, A2, A3 plus 3 times A1, A2, 3 times A1, A3, 3 times A2, A3, 5A1, 5A2, 5A3 plus 3. It's constructed in a weird way. And if you say that, I will completely agree. All right. But this is my construction. All right. I love it. So you have to accept it. All right. But so this is a particular way to give you another example, because I prefer giving examples after examples after examples at any level, at the PhD 5th year level or undergraduate 1st year level. It's no problem. If we work a little bit harder, we can give examples, no problem. And students understand. Sometimes we misunderstand and we tell them that you won't understand this. You need measure theory. You don't need measure theory. All right, even though I love measure theory. So simple does it. So this is a joint distribution. You can check easily. This is between 0 to 1 cube, and I conceptualize x1, x2, x3 with this PDF. And now again, because of symmetry, there is a symmetry here. You have to discover that by yourself. And then what you can show, the marginals are still 1/2, 1 plus A1 for each one, A1, A2, A3, all right? And then pairwise, Ij, if you integrate the 3rd variable out, you will still have it is the product. It will take you a little bit more time than the other example. So that's why I call this class 2 of new examples. But you have to be patient, very simple integrals. I don't want to make mistakes. So for example, here, of course, you will get 5 if you integrate all variables. If you integrate with respect to all variables, you will get 3 times 1 times 1, and x3 will give you 1, so 3. So you have to take care of those, all right? And then pull all the constants, and you will see in just 1 minute, if you spend 1 minute, that Gij will be exactly the product of these Gi's, pairwise. So what that means is Xi, Xj's are pairwise independent, all right? Are pairwise independent. But again, Xi, Xj, Xk, the three, X1, X2, X3 are not independent. Why not? Because first of all, you have to have 1/8 outside. I don't have 1/8 outside, all right? Second of all, when you multiply them, it will be, you will have A1, A2, A3, A1, A2, A3, A1, A2, A1, A3, A2, A3. You won't find these 3 times this, 3 times this, 3 times this, 5 times this. You won't have that, because this has to be just 1/8, and they all have to be 1, all right? So you can easily show that G3x is not the product of G1x, G2x, G3x, I mean x1, x2, x3, for some x1, x2, x3 in 0, 1 cube. That will show they are not independent, all right? This example, again, I call it simple, I call it pretty, I call it easy, and some of you may think it's trivial, but it is easily understood. It's a very easily understood construct, but very different from the trivialities of my head, tail, head, tail. And you can't find any other example almost in almost any textbook. That's the only example we live with. And you can have so many more examples here. So again, you can pick any arbitrary functions, all right? Non-negative functions in the appropriate spaces, unrelated, and create densities out of them, integrable functions. That's all. So again, I show you some functions here. Same functions will work that I had before. If you have 2 minutes to spare, you can have another example. If you have 2 more minutes, you can have another example. You can have millions of examples. Okay. 3.3, class 3 of new examples. Class 3 of new examples. All right. Now so I say more breadth. So let us take a pause now, just as a very brief pause, and let us think what I have shown you so far. I have shown you this particular example. This was my class 1 example. I have shown you a function of 3 random variables where the marginals were 1 plus A1, 1 plus A2, 1 plus A3, separate, multiplied by 1/2, 1/2, 1/2 in the spaces 0, 1, 0, 1, 0, 1, respectively. All right. But the joint product of all 3 is not that. Now, let us rethink about this example. Again, I have shown that the marginals are same as before, 1 plus A1, 1 plus A2, 1 plus A3 multiplied by 1/2, 1/2, 1/2. And the marginals are the products, all right, Ai, Aj, for any I not equal to j in the appropriate spaces, 0, 1, 0, 1, 0, 1. And they are not, this here also x1, x2, x3 are not independent. In the previous example also they were not independent. So here is a nice idea. Here is a very nice idea. Think of this. So I consider that f3x I showed to you defined on 0, 1 cube, and this g3x I have defined on 0, 1 cube. They are well defined. You can take any a1, a2, a3 functions, PDFs between 0 to 1, or some other space, and then take a convex function of those. So h3x is alpha times f3x plus 1 minus alpha times g3x. 0 less than alpha less than 1. So this is a class. This is now a large class of density functions, PDFs, on 0, 1 cube, which are given by h3x. Because this is the density and that's the density, alpha between 0 to 1. But think of the magic. When you integrate f3x from f3x, when you take the marginal of x1, you have 1/2 1 plus a1 x1. From this, when you take the marginal of x1, you have just, that means marginal means what? Integrals. So you integrate x2, x3, and integral is 1/2 1 plus a1 x1. So alpha times 1/2 1 plus a1, 1 minus alpha times 1/2 1 plus a1 should be 1/2 1 plus a1 x1. So h3x has the same marginals as f3x and g3x, which were actually 1/2 1 plus a1, 1/2 1 plus a2, 1/2 1 plus a3, correspondingly x1, x2, x3 between 0 and 1. But now I have a huge class of distributions between 0 and 1. They are different from f3 and g3. So you see, we are continuously enlarging our sets of examples. So now I can have a much larger class of examples, a lot more than I had before, and the marginals are exactly the same as before. How about the two-dimensional marginals? Say x1, x2. So x1, x2 means from here, you have to integrate x3 out. What is the answer? I showed to you. It will be 1/2 1 plus a1, and then 1/2 1 plus a2 times alpha. That's what it will be. So, and then from here, if I do x2 in integrate x3 out, I will have 1/2 1 plus a1, 1/2 1 plus a2. a3 will be out. So when I add them, I'm going to have 1/2 1 plus a1 times 1/2 1 plus a2. So x1, x2 will be independent. Similarly, you can show x1, x3 will be independent without doing any integrals. You can show x2, x3 are also independent without doing any integrals. And again, you can show that x1, x2, x3, by the way, are not independent. So again, you can conclude for every I and j, xi, xj are independently distributed. Simple construction. Like I tell my students in my classes at any level, simple does it. All right. A lot of times we ignore simplicities. Simple can be very pretty. All right. So xi, xj are independently distributed for any ij between 1 and 3, but x1, x2, x3 are dependent. All right. So again, so it opens your horizon. All right. You can do so much more. Students can experiment, and you can compare these various joint densities and see how different they can be. But you have pairwise independence, but not mutually independence. All right. But still, there are problems. There are problems. What is the problem? Now I know that there will be smart students who are attending my lecture, and they will say, Professor, these are examples of 3 random variables. All right. This is a density function of 3 random variables. And I constructed this. All right. I constructed that. That's my construction. So how did I do it? Well, good luck. All right. I did it. So I'm lucky. I'm just lucky. So I did that. Okay. And now you can fool around with it. Similarly, I did this, right, in my textbook. And again, I was lucky. So that's another example. And then you can take convex combinations, and you can have hundreds and millions of, more of similar examples by varying AIXIs and the spaces. You see, space between 0 to 1, that's not a big deal. You can always take other spaces. You have to appropriately take weights here. That's not a big thing, big issue. All right. So a smart student in attending my lecture now will say, well, Professor, these are all examples of x1, x2, x3. How about x1, x2, x3, x4? How about x1, x2, x3, x4, x5? How about x1, x2, x3, x26? Right? And then I have to sit straight. I say, well, there's something to think about. But the point is, this example here, right here, G3x, there is an inbuilt symmetry here. I told you, you have to discover it, what it is, all right? Then you may try to do it for 4, but I can tell you it will be hard, all right? So similarly here, there is an inbuilt, inherent symmetry. And if you want to replicate that with 4, 5, 6, 26, you will be hard pressed. You will be hard pressed. All right. But the question still makes sense. If somebody asks me, how about 6 variables? How about 59 variables where all 58 sub vectors are independent, right? But 60, all 60 together, they are dependent. You see what I'm saying? So you take 100 variables at a time, 100 variables altogether, 100 dimension, all 99 sub-vectors, they consist of independent variables. But as soon as you put in the last variable in, they become dependent. So when you ask me how to generalize it, if you ask me, or if you are thinking about it already, that's what I should do. That's what I must show. All right. So that's what I'm going to do next, because I don't think you should let me go without doing that. All right. Because otherwise the lecture remains incomplete. I want to help my students, colleagues, and young researchers and so on. I'm not helping a whole lot. I'm closing the window with 3 variables. Here are my generalization. All right. I will again say natural generalization. Natural generalization. So I say I have q plus 1 variables. All right. Q plus 1 variables. And then if you take any q subvector from q plus 1, you take any q variables subset from those variables, they should be independent. So that is, I call q-wise independence. So when q equals 2, you get pairwise independence. So I consider q plus 1 random variables together. I take not just a particular q set, q subset. I consider all q subsets. But then as soon as I make it q plus 1, the last variable, the one that I left out, they become dependent. So generalization is q-wise independence may not imply q plus 1 independence. A generalization. So here is your obvious definitions. I define pairwise independence. I define mutually independence for 3 variables. Now it is for q plus 1 variables. So x1, x2, xq plus 1 are q-wise independent if and only if every q tuple, so that means you take subset of size q from x1, x2, xq plus 1, any q tuple consists of independently distributed random variables, whatever be the q indices, I1, I2, iq, they are different between 1 and q plus 1. And q is 2 or more. So if q is 2, I have already finished my lecture, that part of the lecture. All right. So that is q-wise independence. What is mutually independence in this case? Well, same idea as before. Same idea as before. You have to have q-wise independence. All right. So lower dimensions should be all independent, any subset, q-dimensional, and also q plus 1 of them, when you take their joint density, should factorize for all x1, x2, xq plus 1 in the appropriate q plus 1 dimensional support. These are natural definitions extending pairwise independence and mutual independence for 3 variables. All right. So let me work with that little bit. So previous constructions were for q equals 2. Now we fix q plus 1, positive, symmetric. I will consider now only symmetric variables. I showed in my first slide or second slide, I showed you can easily construct symmetric variables. You know, when I ask some students, beginning students, give me a symmetric density, they always give me normal density. I say, come on, are you kidding me? So is that the only symmetric density you know? I can construct 30,000 symmetric densities in the appropriate space. All right. So why only normal? Then they will think about it and they will say, okay, Cauchy. That's it. That's it. Normal and Cauchy, they're the only one symmetric. Then the who are very smart, they will say, okay, Laplace, that's a symmetric density. But again, you are not expanding your view. You are not expanding your depth of field. All right. So you can construct any symmetric density. There are hundreds and thousands and millions of them. Take any q plus one of them in an interval like minus c to c. So it has to be symmetric. So it is between -1 to 1 or -2 to 2 or -3 to 3. All right. I want in a finite interval because my integrals have to be done easily. I don't want Cauchy density. I don't want normal density. I don't want, like folded exponential like Laplace. All right. I don't want to do that. I want simple. Simple does it. So you take simple, very simple symmetric functions in an interval negative to positive something, and their densities. Oh, this is not right. That's a bad typo. So this. Oh no, this is okay. So these full integrals are one because they are densities. Then because they are symmetric, and with the functions that I will have, not all. This is not always true, but this integral I'm expecting to be 0. X times bi x will be 0. It is not always true, but there are hundreds and thousands of symmetric densities for which x times bx integral -1 to 1 is 0. You can easily construct, all right, any number of them. But this is obviously not always true. For example, for Cauchy density, if you take minus infinity infinity x times Cauchy density, that is not 0. Even if it is centered at 0, the mean doesn't exist. But I'm assuming it is 0 because I'm considering very simple functions. You will see that. So each bix is symmetric in this interval with 0 mean sitting on this support. Now I will construct my bix from that function. This is a specific example. I take this function. Don't get nervous with these constants. This is just to make the function a density function. That's all. So basic function here is x to the power 2 delta I. That's all. X to the power 2 delta I. So it is x squared, then exponent delta I. So x squared is positive. So it's a symmetric function, all right, in this interval. And this is a constant. Constant is appropriately found using simple integral, and so that the full integral is 1. So these are my densities I'm going to work with. Again, you can work with your densities, any one of them, all right? So there are q plus 1. And then I'm giving you my f density of q plus 1 random variables. I have q plus 1 densities. I have joint density of q plus 1 random variables. It is now done in a peculiar way. So here is the product of all the densities. You can see that bixi I equals 1 to q plus 1. If you don't have this first part, if you don't have that first part, you have all of them independent. All of them will have independent. So that's not what I want. So that's trivial. So you don't want that. I don't want that. I want non-independent variables, at least. All right, all of them together. And so I fudge it. I multiply by 1 plus something. So it's constant. And then product of xj's. Now, intuitively, this c to the power this, that makes it, that gives me another way to vary the examples. And this product should be important. But here you notice this is xj, not xj squared. This is xj. All right. So these xj's will be important. I will show it to you. So first thing first. So this is a construction. One can show easily that this multiplier right here is always non-negative. All right. That's why this c comes in. You can argue if you are not working with a pen and paper, you will say, well, of course, product xi can be negative, and so this can be negative. No, this cannot be negative. You can show by taking the absolute value. All right, absolute value will be bounded by appropriate number here, and that's how I adjusted my constants. So this will always be non-negative. So this function will always be non-negative. And then the integral, look at the full integral now. Full integral now will come from, two parts. There will be two parts. One is 1 times this and the full integral, and this times this full integral. All right, because it's two pieces. So I have to do that, and simple integrals. So full density, full integral. So this is the first part, and this is the second part. The first part, it is as if x's are independent. So the full integral will be 1. All right, because they will break up into marginals. The intervals, the supports are unrelated. Remember I mentioned that supports are unrelated. So first integral will be 1. Second integral, what is going to happen? Well, you have the product of xi's. So this product of xi's now comes inside. So it is x1, x2, xq plus 1. So x1 goes with b1, x2 goes with b2, xq plus 1 goes with bq plus 1. So second integral can be split like that. Forget about the constant. Split like that. xi times bix. But I have assumed this is 0. All right. For this function, you can show this is 0. X times this integral minus c to c, it will be 0. All right. It will take you 1 minute, half a minute. All right. So that will be 0. So this part contributes nothing in the integral. So full integral is 1. So it's a density function. It's a joint PDF on minus c to c raised to the power q plus 1. All right. So this is a joint density. Now think of x1, x2, xq plus 1, xq plus 1. I'm almost done. Q plus 1 dimensional random variable. Now you can take marginals of q variables. So from x1, x2, xq plus 1, remove x1. From x1, x2, xq plus 1, remove x2. From x1, x2, xq plus 1, remove xq plus 1. So these are the usual notations for those. I borrowed it from linear regression, like one variable out notation. All right. So just think about it. If you want density of x1, x2, xq, what should you do? If you want the density of x1, x2, xq, then you should multiply with the variable that you are leaving out, right? So when you leave out that variable, again, the integral is very simple. So first part will give you this, and second part will give you this times the integral just for x1, xi, or x1. And this integral is 0. So this will become this when j is not equal to I. So if you look at marginals of just xq, x1, x2, xq, not q plus 1, or x1, x3, xq plus 1, and all those, their marginals would be product of those bi's. So they will become q-wise independence. Q-wise independent, all right? But you can see that just right here. You can see that, all right? The q factor, q of them will have this as the joint PDF. So they are q-wise independent. But all put together, they are never going to be independent. Why not? Because of this part. 1 plus c times minus, etc., that you will never recoup from independence. So they will not be independent. So this is a very broad sense of extending the notion of pairwise independence and mutual independence. And pairwise does not imply mutual as regards to independence. And similar is true for q-wise independence and q plus 1 independence. They don't go hand in hand. All right. And so one last comment I have is, you can see what is going on, what kind of game I'm playing. Here, for example, I have product of xj's. So x1, x2, x3, xq plus 1. So you can see where that comes from. That multiplied with this, the second integral, becomes zero. Whether it is multiple integral or whether it is univariate integral, they become zero, all right? Because this density function is symmetric. So you can take any bounded function here, that is an odd function. Because any odd function and a symmetric function integral is not necessarily zero, because Cauchy example is right there in front of you. So I'm not saying that, but the kinds of examples I have, you can easily take any odd function here, and BIXs, which are in bounded space, they will be zero. So you can really fool around and replace this with, for example, these kinds of functions where DIs are odd integers, not just one. It may be 5. You will have another example. You can take sine of xi di, because sine function is odd, all right? But it is bounded. It is bounded. So all these examples will work just fine. If you sit down with half hour, you got every example. All right. So concluding thoughts. A reader is no longer stuck with one kind of stale example and its trivial variations. All right. So you are not. You have seen so many examples, so many classes of examples. I have shared numerous examples. I have explained a number of useful constructions. Anyone should feel free to explore more. I actually invite you, especially my junior colleagues, my uh, um, students, friends, and anyone else who wants, who want to deal with this. Explore more. Explore more. New examples can become productive, instructive. This is the last one is my philosophy. New examples can become productive, instructive, pretty, and fun. All right. Selected references. These are some of the textbooks I have checked, and many more. All right. You know many of them. All right. Kassela-Barger, Hoel, Porton, Stone, Hogan, McKean, and Craig. This is a master's level textbook that came from Hogan Craig's book. My textbook has that first example, not the trivial example, the other construction. Ross's book has the same example, the trivial example, with just minor modification. Authors think that they can fool you. Many authors think that they can fool you. They can give the same example in a same set of fruit in a new bowl, and it becomes a different set of fruit. It does not. It does not. So you have to question. So Schiffer's book has the same example. Zach's book has the same example, and you can look at my book and my textbook if you have any chance. It has that first non-trivial example that I gave, class 1 example. All right, and I thank you all, and I'll be happy to answer any questions or comments. If you need any more information, please feel free to send me an email. I'm a very friendly guy. I will reply. May not be just immediately today, but I will reply to you. Just have patience, and I will be happy to talk to you and take any questions or comments. Okay? So I will stop sharing.
We would like to express our sincere thanks to Professor Mukhopadhya for taking time out of his schedule and giving us such a wonderful exposure on pairwise independence and mutual independence and its generalization through some very interesting examples. We'll now have a short question answer session. I'll request the participants to write their questions to the speaker in the comment box.
Don't be shy.
Right, we're waiting for your questions.
No problem. Don't be shy. Every question is important.
So we have a question from Tuhin Shubha. Can you see the question, sir?
I saw it, it just went away very quickly. But it is I saw that there was a question about 1/48 Sam something.
Right,
Yes, but if that works, that works. I cannot say right now if it works or not. But if it works to him, that's fantastic. Sure. So you have another example to discuss with your students. Fine. Absolutely great. I love it. But I cannot check right now whether that is, but I'm sure you have checked. So I trust you.
Thank you, Tuhin. Any more questions? Okay, Omkar has got a question. The interplay
Sure.
between the classes of examples and the simplicity underscore the critical thought process beneath those creations of the densities and finally the generalization. So could you please advise what would be the formal way to make those examples at the first place? You showed plethora of ways to make variations of the discussed examples, but what would be in general the approach to conjure up these things?
Then in that case, I would that there is nothing that I know of. Um, uh, some days some things bother me, and then I try to resolve in my way, and then get some new examples, new counter examples, or new explanations, or something like that. I don't think one day I thought I would sit down and do some of these things. And the examples that I got, they were just by chance. So trying an error, and if I pick all the densities one, it's of course not going to work. So I had to vary things suitably, and I have to take products, of course. So and then I pulled around 1 day, 2 days, I don't know how many days, and not like every 24 hours a day. Some days I will leave it for 1 year and then come back, and it will again bother me, and then I will do something else. So there is no general approach to come to my class 1 examples or class 2 examples or class 3 examples. Like Tuhin Shubra looks like he has already another example. So in my class 3 example, where I took the convex combination, you can have more examples there, which will be good. But any general thought would come from my last topic. Last topic tells you what I was thinking originally, but I could not pinpoint it. Last example, it gives you the last construction, the Q-wise independence, but it does not give Q plus 1 independence. But so there, if you take Q equals 2, you will see the exact picture. If you take Q equals 2, you can see why this construction works, how this construction works, and why this is a natural way to do it. The class 1 examples, I would say they are not natural. I will accept that. Class 2 examples are also not natural. The generalization that I have given you with Q equal to 2 will be a natural way to generalize this thought. And that did not come the first time I did class 1 example or class 2 examples. Class 2 example was actually very recently. I was again fooling around. Because of this talk, I was fooling around and I found class 2 examples. Then I thought of convex combination because they gave the same marginals. But on the other hand, same marginals and same two-dimensional marginals also. So that worked well. But on the other hand, the real key is the generalization idea. There, if you take Q equals 2, I think you will know in 5 minutes why and how one should construct an example. What kind of examples would work? What kind of examples will not work? That 1 plus something, that is very crucial. And then the outside the product of the densities, that's very crucial. And the xi times bi integrally 0, that's very crucial. Nothing else is crucial. So that's what opens up a window. That's what opens up a new door. So if you ask for a general thought, that I cannot pinpoint anything in particular that led to this. Okay, so I will leave it. I will leave it at that. I wish I could share more.
So if there are no more questions, let's thank the speaker once again. We would like to thank all of you for actively participating in today's lecture. Hope to meet you soon with the next lecture in this series, which will be announced in due course. Till then, stay safe.
Thank you to all the organizers and the participants. I appreciate. Thank you.
Sir.
Stay safe. You all stay safe. Thank you.
Thank you, sir.
Thank you
Thank
for
you, sir.
attending.